Hello friends, in this video we are going to study about the controllers used in the control system. So let us start with our topic. If we see the block diagram of a closed loop control system, then it is like we have the input signal, then output signal, we have a feedback, and we have the controller and the plant. So let's see the block diagram of a closed loop control system. This is our input RS and this is the output CS. It is the error detector. It is the control logic elements. So this is the block diagram of a closed loop control system. Now in this block diagram, the work of the error detector is to get the difference of the desired input. This is the input which we desired and this is the output or the feedback signal. So what this error detector does, it calculates the difference or the deviation of the output signal from the desired input. Okay, this is the feedback signal. So it sees that how much our output is deviated from the input and it produced a signal. This signal is called the actuating signal. And this actuating signal is then given to the control logic elements. So this complete setup, the error detector plus this control logic elements, they are collectively known as a controller. So how we can define this controller? A controller is one which So we can define the controller as a controller is one which compares the controlled values with the desired values and has a function to create the deviation produced, to correct the deviation produced. So what a controller is doing, it is comparing the desired input and the controlled input. This is our controlled input and this is the desired input. So controller is comparing these two inputs. It is checking that how much the controlled input is deviated from the desired input, and it has a function to correct the deviation which is produced. So this function, it can be different. So depending upon the function, there are various types of controllers. Okay, the controllers can be like analog controllers are there, digital controllers are there, depending upon the function which is used to correct the deviation. So this is how we define a controller. Now let us see that what are the uses of controllers. The first use of controller is that it improves steady state accuracy. Okay. And how they can improve the steady state accuracy? By reducing the steady state error. the steady state error is decreasing and accuracy is improving, so the stability also increases. Now, controllers, they also help in reducing the offsets in the system. And maximum overshoot, it can also be controlled by using the controllers. Controllers also help in reducing the noise in the system. So disturbances can be removed using the controllers. Also, if the response of the system is slow, then it can also be improved. That is, the response of the system can also be improved, or it can be made faster. So these are the uses of the controllers, why they are used in the, for these reasons they are used in the control systems. So first is the that they improve the steady state accuracy, and because accuracy is improved, so stability is also improved. Also, it helps in reducing the offsets in the system. Maximum overshoot of the system can be controlled. It helps in reducing the noise signals produced in the system, and also it helps in making the response of the system faster. Okay, so these are the reasons why the controllers are used in the control system. Now, let us study the various types of controllers used in the control system. Now, these controllers, they can be divided into two parts, like analog controllers and discrete controllers. Analog controllers, because we have studied like in the definition of the controllers, that the controller, it has a function. So this function can be an analog function or it can be a discrete function. So if it is an analog function, then the controllers are called analog controllers or continuous controllers, and if the function is discrete, then the controllers are called digital controllers. Okay, so first we will study about the analog controllers. Now, in analog controllers, the controlled variable, that is the controlled output, it can have any value within the range of the controlled output. So in analog controllers, the controlled variable Okay, so the control variable can have any value within the range of the controller's output. And if we are using the automatic control scheme, so in the automatic control scheme, the controller is automatically going to compare the controlled output, that is the control condition value, with the desired value, and it will produce a function which is going to affect the output, and it will try to make the output close to the desired output. Okay, so in automatic So in automatic control scheme, the controller, it is going to compare the controlled value with the desired value, and then it will automatically correct any type of deviation between the deviation of the controlled value from the desired value. Okay, and this correction, it is made by a function, and depending upon the function used to correct this deviation, there are three types of controllers. First is the proportional controller, second is derivative controller, and third is the integral controller. Now by the name you can understand that in proportional controller, the function which is used, it is having the proportionality between the functions. Okay, and derivative controller, it will have derivative function, and in integral controller it will have integration function. Okay, so depending upon the function used to correct this deviation, there are three types of controllers. First is proportional, third is integral controller. And there are also controller which is a combination of these three types of controllers. So there are also, we have proportional derivative controller, then we have proportional integral controller, and we have the controller which is the combination of these three controllers like proportional, derivative and integral controller. So it is named as proportional, derivative and integral controller. So there can be these 6 types of controllers are there in the analog controllers. Now we are going to study these controllers one by one. So let's start with the proportional controller. So the first controller is the proportional controller. Now in proportional controller, as we have seen here in the block diagram, that the controller compares the values with the desired values, and it has a function. So here the function is the proportional function. So in this proportional controller, the actuating signal, it will be proportional to the error signal. Okay, error signal is the difference of the reference input and the feedback signal. So this actuating signal is going to be proportional to the error signal in the proportional controller. And what is error signal? It is the difference of the reference input and the feedback signal. Now if we represent the error signal by ET, the reference input is RT, and the feedback signal, actuating signal is EAT, error signal ET, and we have feedback signal. So this actuating signal, it is proportional to the error signal. So we can write that EAT is proportional to the error signal ET. Now if we remove this proportionality sign, then we will introduce a constant here. So EAT is equals to KPET. Okay. That means that the actuating signal is proportional to the error signal. So this is what the proportional controller does. Now what are the conditions where we can use the proportional controller? What are its advantages and disadvantages? Let us see. Proportional controller is used where the error signal is weak and it needs some amplification, because if the error signal is low, the controller is not going to detect it. So this controller is what giving, it is just amplifying the error signal, is used where the error signal is weak and it needs some amplification. Also, it is used where offset can be tolerated, because proportional controller, it introduced offset in the system. So if we want to amplify the error signal, offsets will be introduced if we are using the proportional controller. So it can be used only at those places where offset can be tolerated and load changes are small. So these are the places where we can use the proportional controller. Now the advantages of the proportional controller. First advantage is that it reduces the steady state error. Also, it makes the response of the system faster. And third use of proportional controller or advantage is that maximum overshoot can be reduced to some extent using the proportional controller. So these are the advantages of the proportional controller. Now disadvantage of proportional controller is that maximum overshoot is increased. Now here I have written that maximum overshoot can be reduced to some extent, and here I have written that it makes the response of the system faster by increasing the forward path gain. Now if we increase the forward path gain, the maximum overshoot is further increased. So it is decreasing the maximum overshoot, but at the same time, due to the increase in the forward path gain, the maximum overshoot is again increased. So disadvantage is that maximum overshoot is increased when forward path gain is increased. So these are the advantages and disadvantages of proportional controller. Now if we see the block diagram representation of this proportional controller, then it is like we have the error detector, then we have controller. Because it is a proportional controller, this was our reference input, that is RS. This is the actuating error signal. Error signal is ET, so its Laplace transform is ES. And this is our controller. Now here we have proportional controller and its proportionality constant is Kp. So this is our proportional controller. Then we have controlled system, or we can say plant. So the transfer function of plant is GS. This is our feedback signal. Feedback element will have the transfer function as HS. This is the actuating signal. So you can see that this actuating signal is proportional to the error signal. This is our output CS. This is feedback signal. And error signal is equal to the difference of the reference input and the feedback signal. So we have put here negative sign. So this is the feedback control system with a proportional controller. Okay. Now next type of controller is derivative controller and integral controller. Now let us study about them. Second, we have derivative controller. Now just like proportional controller, it was having the proportional sign. So derivative controller means that the actuating signal is equal to the derivative of the error signal. It means that actuating signal was EAT and it is equal to the derivative of the error signal. And in the block diagram where we have written KP, so here the proportional, or we can say the constant, will be KD. Okay. Similarly, for like we have the derivative controller here, the constant is here the derivative, this KD, derivative constant. And if we draw the block diagram, then here we have the error detector. So the actuating signal is equal to the derivative of the error signal, and here we have the constant as KD. Now third controller is integral controller, and in the integral controller the actuating signal is equal to the integral of the error signal. So we have the actuating signal EAT and it is equal to the integration of the error signal. Okay, it is equal to this. Now here if we write the constant, so it will be Ki integration of ET dt. This Ki is the integral constant, and if we draw the block diagram, then we will have here we have the constant as Ki. So these are the three basic types of controllers: proportional controller, derivative controller and integral controller. Now there can be combination of any two types of these controllers, or of these three controllers we can have. So let us study the combination of these controllers. First we will study proportional derivative controller, and it is also known as PD controller. P is for proportional, D is for derivative. So it is also known as PD control. Now here the actuating signal, it will be proportional, or it will consist of both the proportional error signal and also the derivative error signal. Okay, so it has both the proportional error signal and the derivative error signal. So if we write the actuating signal, then actuating signal is EAT and it is equal to the proportional error signal, that is ET, plus we have the derivative KD d ET by dt. Here we have the constant Kp also. Now if Kp is equal to 1, then it can be written as EAT equals to ET plus KD det by dt. So it has both the proportional error signal and the derivative error signal. That is why it is called proportional derivative controller. Now if we draw the block diagram, then it will be a combination of these two controllers. So let's draw it. Here we have a unity feedback system, so we have taken Hs equals to 1. Now here representation is in Laplace transform, so when the derivative is represented, we have multiplied it with s. So we have written here kds. Now this is due to the proportional controller and this is due to the derivative controller. So we have combined these two, we have added these two signals, and this is completely known as the proportional derivative controller. Now this is the difference of the feedback and the reference input is the error signal ES, and when we have applied the controller over this signal, so it will be known as GCS, that is the controlled output. Okay, output we have controlled here. So this is complete the proportional and derivative control action. Now this GS can be the transfer function of the system. Now if we take a second order control system, then its transfer function is, we have the standard form of transfer function of a second order system as CS upon RS equals to omega n square upon s square plus 2 del omega n s plus omega n square. This is the transfer function of a second order system. So if we keep this transfer function here, then this proportional and derivative action will be applied on the second order control system. So let us draw the block diagram for the second order system. This is the transfer function or the gain of the plant, and this is the controller gain. Okay, so it is GCS and this is CS. So now let us derive the overall transfer function of this system. This is what a feedback control system with PD controller, that is proportional and derivative controller. Now let us derive the transfer function. Now this transfer function is what? The ratio of CS by RS. So CS by RS, it is equal to, so its transfer function will be 1 plus GS, that is GS upon 1 plus GS, which is the transfer function of a closed loop control system, we have GS upon 1 plus GS HS. Now here HS is 1 because it is a unity feedback system. So GS will be the multiplication of GC and GP. Okay, GP is the gain of the transfer function of the plant, and GC is the transfer function of the controller. So here we have KP plus KDS because they are added up. So we will have KP plus KDS, and this is multiplied with the transfer function of this plant. So this is omega n square upon S plus 2 del omega n. This is GS upon 1 plus GS HS. HS is 1, so we will just write GS here. So this is the transfer function or the overall transfer function of this system. Let us simplify this. We will have CS upon RS equals to So this is the transfer function of this system. Now if we see that this is the modification of the second order control system transfer function. The transfer function of second order control system is CS upon RS omega n square upon S square plus 2 del omega ns plus omega n square. Here omega n square, this is the additional term which is multiplied with this. Then we have S square plus S. Now here the coefficient is 2 del omega n, and here we have 2 del omega n plus kd omega n square. Here we have omega n square, here we have kp omega n square. So this is the difference between the transfer function of a second order control system and a control system where we have applied the proportional and derivative controller. Now the characteristic equation of this system, if we write, then the characteristic equation is given by characteristic equation is what? It is the denominator polynomial which is equated to 0. So this is the equation. We have S square plus S So we have equated this denominator polynomial to 0 and it has become the characteristic equation. Now here the damping ratio is this given by two del dash omega n is equals to, if we compare this with 2 del omega n with this coefficient of s, then here del is what? Del dash, and this will be equal to 2 del omega n plus kd omega n square. Now from here if we calculate the del dash, then it will be So this is the damping ratio, the new damping ratio due to the proportional and derivative controller. Okay. Now, if we calculate the steady state error for ramp input, which is applied to the second order system, then the steady state error is given by the formula for the steady state error is ESS equals to limit S tends to 0 SES. And here we have to calculate the steady state error for unit ramp input. So for unit ramp input, RS is equals to 1 upon S square. Input signal is T. Okay. So steady state error, we know that this ES upon RS is what? 1 upon 1 plus GS HS. Okay. So if we calculate this ES, then it will be RS into 1 upon 1 plus GSHS. Now RS is what? 1 upon S square. So put here 1 upon S square and then put the value of 1 upon 1 plus GSHS. 1 plus GSHS of this system is, this is our transfer function. Okay. So 1 upon 1 plus GSHS is this. So we will substitute its value here. Yes. So we have substituted the value of 1 plus GSHS here. Now this is S square, this is S, and we will put the value of this ES in this formula for the steady state error. So the steady state error, that is ESS, is equals to limits S tends to 0 SES. Put here the value of ES. We have 1 upon S square. This is S. So S we will write here. Then S is plus 2 del omega n. Now this S square, S, they are cancelled out. So we are left with this term. Now apply the limits here. This will become 0 plus 2 del omega n. So we have 2 del omega n only. Here this is 0. This term will become 0 and only this term will remain. So ESS, it is equal to 2 del omega n, and in the denominator we have omega n square kp. Omega n cancelled here. So ESS is equal to 2 del upon kp omega n. This is the steady state error of this system having proportional and derivative controller, and the input is the unit ramp input. Okay. Now where are the places where we use this proportional and derivative controller? Let's see. The proportional and derivative controller, it is used where the minimization of the amount of deviation is required. Okay, that is the deviation cost, deviation of the controlled output from the desired input is minimized. Okay, so first use is need of minimization. So the proportional and derivative controllers, they are used where the need of minimization of the amount of deviation caused by the plant load changes are required. Also, it is used where the maximum overshoot has to be reduced. Now, the advantages and disadvantages of this proportional and derivative controller. Advantages are that one of the advantages is that maximum overshoot is reduced. And also the rise time is decreased. The disadvantage of PD controller is that the steady state error is unchanged for the RAM input. We have calculated here the steady state error. So the steady state error is unchanged for RAM input. Because in the steady state error, the formula which we have get ESS equals to 2 del upon Kp omega n. So this steady state error, there is no function or no variable involved here which is changed. So this remains the same for the RAM input, and it is the disadvantage of the PD controller. Now the next type of controller combination is the proportional integral controller. That is, it is the combination of the proportional controller and the integral controller. So let us study about the PI controller. Now in this PI controller, the actuating signal, it is the proportional to the error signal also, and it also involves the integral of the error signal. Now if we define this actuating signal or we write the formula, then it will be, this is the actuating signal EAT, then it will be the sum of the proportional error signal, that is KPET, plus the integral of the error signal. This is the integral constant and this is the proportional constant. If we keep Kp equals to 1, then this actuating signal will become okay. Now let us again draw the block diagram for this proportional integral controller. Again, we are considering here a second order system. So this complete the proportional and the integral controller is collectively known as the PI control. PI controller. This is Kp for the proportional controller and this is Ki and the integration function for the integral controller. And this is applied on this signal. So the output signal, that is the actuating signal, it will be the proportional error signal plus the integral error signal. Now let us derive the overall transfer function of this system. So the overall transfer function will become, now when we apply Laplace transform on this integration, it will become Ki upon S. Okay, so this is Kp plus Ki by S multiplied with this transfer function. Then we have 1 plus this GS HS is here 1 because it is a unity feedback system. So again we will write GS here. Now let's simplify this. We will get So this is the overall transfer function we have get. Now just write the characteristic equation. So the characteristic equation is given by characteristic equation is the denominator polynomial equated to 0. So this is the denominator polynomial and equated to 0. Now the error signal, it is given by ES by RS 1 upon 1 plus GS HS. GS is omega n square Kp plus Ki by S divided by S square S plus. Simplify it, we will get ES equals to RS this will go in the numerator and in the denominator we will have S square S cube S square into S cube plus S square into 2 del omega n So this is the error signal. Now here we can take different types of inputs. So we will consider here the error signal for the unit parabolic function. We will calculate that what will be the error signal for this. If it is a unit parabolic function, then Rs is equal to 1 by S cube. So we have ES equals to RS. Into this, put the value of RS. This is 1 upon S cube. And we have the transfer function here as so this is the error signal. Now let's calculate the steady state error for this. So steady state error signal is ESS limit S tends to 0 S ES. This is the steady state error. Substitute the value of ES here and apply the limits. So let's apply the limits here. we have s cube is s square, so this will be cancelled out. And let's apply the limits. S tends to 0, so this will become 0 plus 2 del omega n. This is 0, this term will become 0, this is 0, and this is ki omega n square. So the steady state error will be 2 del omega n upon ki omega n square. So this will be cancelled and it will become 2 del upon ki omega n. So this is the steady state error for a unit parabolic function when the system is having the proportional and integral controller. Now let us see that where we can use the proportional and integral controller, what are its advantages and disadvantages. Now proportional integral controller, it is used where high accuracy is required. Offset should be eliminated. And integral saturation So these are the places where we can use the proportional and integral controller. Now advantages and disadvantages. Advantages of proportional integral controller is that the system accuracy is increased. That's why it is used where the high accuracy is required. So the advantage of PI controller is that the system accuracy is increased. Also, it eliminates the offset. That is why it can be used at the places where offset must be eliminated. So offset is eliminated. Also, steady state error is minimized. Now, disadvantages of PI controller is that as the order of the system increases, the stability decreases. Also, there is no improvement in the transient response of the system. And also the PI controller cannot be used at places it is not suitable for rapid changes. That is when the system is having, the input is having rapid changes in it. So at that places the PI controller cannot be used. So this is about the proportional and integral controller. Now the last type of controller, it is the combination of all the three controllers: proportional controller, derivative controller and integral controller. So it is known as proportional integral derivative controller, that is PID controller. This is very important controller and most of the time it is used in the control systems. So let us study about it. It is known as PID controller. So it consists of three terms: proportional, integral, derivative. So the actuating signal, it is the proportional error signal also, it is the integral of the error signal and the derivative of the error signal. So it is the combination of all the three types of signals. So we can say that the actuating signal So it is the sum of three terms. Now if we define the actuating signal, so it is EAT equals to KP ET, that is the proportional controller. Then integral, we have KI integration of ET dt plus KD and derivative of the error signal with respect to T. So this is proportional, this is integral, and this is derivative. Now let us draw the feedback control system having these three controllers. So this is the block diagram of a feedback control system which is having this PID controller in it. KP is for the proportional controller, KD is for the derivative, and KI is for the integral. And this GCS is the transfer function of the controller, and GP is the transfer function of the plant. RS is the input and CS is the output. ES is the error signal, and here we have a unity feedback system. So here HS is equals to 1. Now if we write the overall transfer function of the system, then it is given by the ratio of CS and RS, and it will be the multiplication of GC and GP. And because we know that for a unity feedback system, the transfer function is GS upon 1 plus GSHS. Here HS is 1 and GS is what? It is the multiplication of this GC and GP. So we will write here the overall transfer function of the system will be CS upon RS, KP plus KDS plus KI by S. So we have KP multiplied with this omega n square and we have 1 plus GS HS also. So this CS by RS will become S square KD plus SKP plus KI So this is the complete transfer function of the system which is having the PID controller in it. Now here the KP is the proportional constant, KD is the derivative constant, and Ki is the integral constant. Okay. Now what are the advantages of the PID controller? Why it is used in the control systems most of the times? Okay, so advantages are first advantage is that it has the advantages of all the proportional, integral and derivative controller, because it is the combination of these three. So all the advantages of these three controllers are combined in the PID controller. Next, it has no offset problem also, and it has high accuracy, high stability, high speed of response. So it is the best controller because it is having the advantages of all the three controllers in it, and that's why it is most of the time used in the control systems for the controlling action. So this is all about the analog controllers. Now let us study the digital controllers. Digital controllers, they are having the function as a digital function. Okay. Now here in the analog controllers, we are using the S domain. So in the digital controller, the function of the controllers will be same. Like there also we are having the proportional controller, derivative and integral controller. But there we will use the Z transform. Like here we have taken the Laplace transform, S domain is used. So there the function is changed because it has become a discrete function. So we will use the Z transform, or Z domain will be used. Otherwise the controllers will be same there, like proportional controller, derivative, integral and PID controller. Just their domain is changed because function is changed there. So we have digital controllers. Now, what are the advantages of digital controllers? Why they are more preferred over the analog controllers? Because digital controllers, they can be designed by computers. So it is easy for the designing of the digital controller is easy as compared to the analog controllers. Also, they give better accuracy, high resolution, and high speed. Okay. So these are the advantages of the digital controllers over the analog controllers. Here also we have proportional, integral and derivative controllers. But we will use here the Z domain, okay, because the function is the discrete function. So we were having KP, KD and KI. We will have here Z, and here also we have a PID controller, which is the combination of these three. And if we draw the block diagram for it, it will be like this is our input. These are the three controllers, KP, this is our output CZ, and this is the input RZ. So here we are just taking the Z transform, otherwise all the operations or all the mathematical operations are same, just like the analog controllers. So in this video we have studied about the controllers used in the control system, the types of controllers, analog and digital controllers, and then we studied the types of analog controllers, proportional, derivative, integral and PID controller. So I hope this topic is clear to you. Thank you.